In 1783, a steam engine was put in a boat for the first time. But for 60 years, engine-powered boats and ships were confined to rivers and lakes. The disadvantage of ships and boats is that once you get out to sea, there are no service stations. So you have to carry all the fuel and supplies you need for the whole journey. No problem for riverboats, which can keep stopping for supplies, but to cross an ocean, steam engines of the time just used too much coal. This boat, the Jaunty, uses a traditional coal-fired boiler driving a compound steam engine, producing about 6 horsepower. And it gets through about 1 bag of coal a day. 6 horsepower is the equivalent of 6 horses pulling you along from the bank. To cross an ocean, a ship would need a lot more horsepower from a much bigger engine and hundreds of tons of coal, leaving no room for passengers or cargo. But people were crying out for a faster, more reliable way to get from Europe to America. A brilliant young engineer finally answered their prayers, a certain Mr. Brunel. Brunel calculated that if you double the size of a ship, the engine only needs to be about 1.5 times the power. For example, take this ship. If you double the length, the width, and the height, it will weigh 8 times more. But the area of hull in contact with the water, comparing this one to this one, will only be 4 times more, and less water resistance equals less power required. So as ships got bigger, the proportion of them needed to house engines, boilers and fuel supplies got smaller, leaving more room for passengers and cargo. And it's this economy of scale that has driven ships to get bigger and bigger ever since. Brunel proved his theory by building the world's largest ship. This is the great-grandmother of all modern tankers, liners and cargo ships, of all the great battleships and cruisers of the 20th century. Brunel's SS Great Britain, now being restored in Bristol, was the first successful engine-powered transatlantic passenger liner. In case you were wondering, the masts and sails were there as an emergency backup for the engines. Brunel's aim was to transform ocean-crossing passenger services from arduous, unpredictable journeys of several weeks into a quick, regular and luxurious experience. The ship had to be big, very big, twice as big as any ship in the world at the time. That's because it needed to carry enough coal for an Atlantic crossing, as well as 252 passengers, 130 crew and 1,200 tons of cargo. Oh, nearly forgot. And a huge steam engine. Brunel calculated that this size and weight of ship was too great for traditional timber construction. A wooden ship of this size would simply collapse under its own weight. So, he took the decision that would change shipbuilding forever. He decided to build his hull out of iron. Fully loaded, the Great Britain weighed over 3,000 tons. So, how on earth do you move that kind of weight with steam engines, which at the time typically drove trains of just a few hundred tons? Brunel's answer, of course, was to build the world's largest, most powerful steam engine. It used 70 tons of coal an hour and weighed 520 tons. It was very inefficient by later steam engine standards, but at the time was an engineering masterpiece. Together with its boilers, the engine occupied 3 decks in the middle section of the ship. The reason why this engine is so massive is less to do with power and more to do with reliability. The fare-paying public was very wary about the idea of using steam engines at sea. A breakdown, a fire, or even an explosion in the middle of the stormy Atlantic was a terrifying prospect. So Brunel chose a low-pressure design for his engine, very low. These boilers, 24 of them in all, supplied steam to these cylinders at just 5 psi, or 5 pounds per square inch. How much is that? Well, a chilled can of cola is about 50 psi. So 5 psi is no more than, say, a gentle kiss. And that's why these cylinders are so massive, to get enough power from so little pressure. Inside those 4 massive cylinders, the pistons produced an impressive 686 horsepower, delivered by a system of connecting rods and chains to the 50-ton main crankshaft. And Brunel made the most of that power with one more radical innovation. With the ship already under construction, Brunel made a last-minute decision to incorporate a new controversial invention, the screw propeller. These days, we take propellers for granted. But in the 1840s, long before aeroplanes, this was seen by many as a strange gadget developed from water pumps. The propeller proved to be a more efficient use of engine power and therefore used less coal. But Brunel had more than just engineering problems to worry about. Despite Brunel's efforts to ensure reliability, the public was still terrified of this steam-powered iron sea monster. A rival German engineer voiced his concerns. He said, "It is feared, and as it appears not entirely without reason, that if the vessel was to be raised at once under the bows and under the stern by 2 waves, the weight of the machinery in the center would break her in 2. The world watched with bated breath as the SS Great Britain set off on her maiden voyage across the Atlantic. 15 days later, she arrived safely in New York with plenty of coal to spare. Brunel had made his point. This was the beginning of a golden era of steamliners, and as public confidence grew, ships got even bigger, and their engines became more powerful and more fuel efficient. This ship has one of the most efficient steam engines ever built. The Waverley is a flat-bottomed pleasure cruiser with paddle wheels instead of propellers to navigate shallow rivers and estuaries. To fit inside the shallow hull, the Waverley's massive steam engine is laid out on its side. Quite unusual, that. Pistons and cylinders this end, massive crankshaft over there, driving 2 paddle wheels, one on either side. Fantastic. This ship has 3 times as much power as the Great Britain, and yet uses far less fuel, thanks to a revolutionary step forward in steam engine design. This is a very efficient type of steam engine. It was developed back in the 1880s and is called a triple expansion engine. Triple for the 3 cylinders that operate at high, medium and low pressure. The steam comes through this pipe from the boilers over there. The boilers produce high-pressure steam, nearly 40 times greater than Brunel's Great Britain. The reason that this engine is both so powerful and so fuel-efficient is that it uses the same steam 3 times. The steam comes through that large pipe and then passes through valves into the high-pressure cylinder, which is the smallest one in the middle. The steam expands, pushing on the piston as it does so. Then on the piston's return stroke, it expels the steam at about 40 psi. That steam, now at medium pressure, passes into a second cylinder, driving a second piston and producing more power. Finally, the same steam, now at low pressure, passes into a very big cylinder where it drives a third piston and produces even more power. Sitting here, I can really feel the power. 700 horsepower in each cylinder. That's 2,100 horsepower in all. Marvelous. This engine runs at about 35% efficiency. That means 35% of the energy in the fuel ends up as power turning the paddles. That's more efficient than most modern petrol engines. I think of the whole arrangement as a recumbent, large, 3-legged person riding a bicycle. On the biggest liners, massive triple expansion engines produced as much as 15,000 horsepower. Their efficiency meant they could carry less fuel and more passengers. And by 1910, the time to cross the Atlantic was reduced to just 7 days. But for some people, that just wasn't fast enough. For the Royal Navy, having the fastest ships in the world was a matter of life or death. And the speed they needed was provided by a new type of steam engine developed in the 1880s.
This new type of steam engine would dominate naval propulsion throughout the 20th century, with a new breed of fast, heavily armoured, iron-hulled ships powered by steam turbines.
'20th century naval warfare was dominated by steam power. Not by massive triple expansion piston engines, but something even more powerful. A type of engine that made ships like World War II cruiser HMS Belfast as fast as any big warship ever built. And that was vital to its success under fire.
In December 1943, Belfast played a key role in one of the most important naval battles of World War II, the Battle of North Cape. She was one of 9 British warships that hunted down a huge German battlecruiser, the Scharnhorst. In terrible sea conditions, it was a deadly game of cat and mouse in which every ship pushed their engine to the limit. Eventually, the Scharnhorst was cornered and sunk. No small thanks to the dozens of men who laboured day and night down here.
The key to the Belfast's victory was her power and speed, and that was provided by steam turbine engines, a late but brilliant addition to the steam engine family.
It's said that James Watt, one of the great pioneers of the steam engine, used to spend endless childhood hours watching kettles boil, fascinated by the steam. But it took over a century and a half before the steam engine moved beyond the idea of pistons and cylinders to something more efficient. An engine that would turn the energy of steam directly into rotational force.
It works by directing a jet of very high pressure steam onto the blades, just like a gale force wind turning the sails of a windmill.
The steam turbine.
Steam turbines were patented by Englishman Charles Parsons in 1884. At first, no one was interested, but Parsons was a persistent man, and he had a plan.
Who be the man with the plan?
Parsons built a 100-foot steam yacht, appropriately named Turbinia, because the 2,100 horsepower turbine engine took up almost the entire length of the boat. Turbinia more or less gate-crashed a Royal Navy review for Queen Victoria, dashing around at over 32 knots. But before furious Navy chiefs could arrest Parsons for high treason, the delighted royal party demanded an encore, and the success of the steam turbine marine engine was assured.
Well done, Turbinia.
The Admiralty bought into the idea and built a new fleet of super-fast cruisers and battleships. And when HMS Belfast was built 30 years later, she was fitted with 4 massive steam turbine engines.
Each of the Belfast's 4 engines had 4 turbines. This is the high-pressure turbine made up of all these individual stator plates or vanes.
Normally enclosed in an airtight cylinder, this turbine was based directly on Charles Parsons' original designs. Each circular plate has over 100 small vanes, against which the high-pressure steam pushed as it passed from one end of the turbine to the other. That's thousands of little pushes that together rotated the turbine at very high speed.
Think of Brunel's pistons turning the engines of SS Great Britain at 18 revs per minute. Parsons' steam turbines turned at 18,000 RPM.
The turbines connect to giant gears which turn the propeller shaft. Each of the 4 propellers could deliver 20,000 horsepower. That's a total of 80,000 horsepower, which gave the Belfast a fantastic top speed of 32 knots, 36 miles an hour. That's getting on for double the speed of the fastest ever piston-powered steamships. But that speed came at the price of a very dangerous working environment for the men down below, because the turbines depended on a constant supply of very high-pressure steam from the boilers.
The steam was superheated, which means it became a pure gas with no water vapor. Dangerous if there was a leak, because it was totally invisible, and at 340 degrees Celsius, pretty nasty if you came into contact with it.
Generating superheated steam was extremely dangerous, because to get the most out of the boilers, the boiler room had to be pressurized and sealed from the rest of the ship.
The room has an airlock. It was kept under pressure by these giant fans sucking in air from the main deck above. The high-pressure air made the boilers more powerful. More oxygen means you can burn more fuel. It was a bit like working inside a giant turbocharger. The downside was that if a tired crewman left both doors open, the sudden change of pressure would cause these boilers to shoot fire right across this space.
So the men down below were at just as much risk as the crew manning the gun turrets. But when you're hunting down a German battleship, maintaining top speed was vital to the whole crew's survival. This ship was as fast as any large Navy ship ever built, and the turbines were also very efficient. Belfast could spend weeks at sea without refueling.
So, for the chap sitting in this chair, that's what you had at your command. A far cry from the steamship technology of the Industrial Revolution. And this ship, HMS Belfast, remained in service under steam power until 1963.
Steam power ruled the waves for over 100 years, and many of the world's largest ships still use steam turbines. Their efficiency of up to 45% and ability to generate huge amounts of power is hard to beat. Petrol engines can't do it, but modern diesels can.
Diesels have been used on boats since 1912. This 40-foot launch has a pair of 215 horsepower six-cylinder diesels driving twin propellers.
Diesel engines can produce even better fuel economy than a steam turbine and just as much power, but with a very different approach.
Diesel engines are designed to operate at low speeds. This one produces its maximum power at 1800 RPM. That means the pistons in the cylinders are rotating the crankshaft 1800 times a minute.
That slow RPM helps both reliability and fuel efficiency. And in recent years, diesel engines have proved capable of providing enough sheer power for any size or shape of ship.
Most ships, like warships, cargo ships and tankers, are long and relatively thin. This one is long and relatively wide. Meet the world's largest container ship, the OOCL Shenzhen.
This ship is the ultimate proof of the Brunel philosophy, that bigger is better. Fully loaded, she weighs 90,000 tons, and 90% of that is cargo. 8,000 containers, 8,000 lorry loads. Everything else is crammed into one small area near the stern. The living quarters, bridge, control rooms, and a 90,000 horsepower diesel engine.
This ship is the direct descendant of Brunel's Great Britain. It's a massive metal ship with a single propeller driven by one massive engine. It's the ultimate economy of scale. The overall power-to-weight ratio is just 1 horsepower per ton. The engine occupies 3 entire floors in the middle of the ship. It's very similar to one of the diesels on our launch, except that every component is about 1,000 times bigger. So here it is, 12 cylinders in a line, driving a single propeller way down there in the stern. You want it massive?
This is a 2-stroke diesel engine, but when you're used to fiddling about with a 100cc motorbike engine in the garage at home, this thing's a bit disorientating. I feel like the Incredible Shrinking Man.
And that's what I call timing chains. This is a spare piston. It weighs 5.5 tons. And that piston would operate inside this cylinder lining, which has a capacity of 2,000 litres. That's 1,000 times a 2-litre car. And this engine's got 12 of them. I wouldn't want to kickstart it.
Total capacity of the engine, 24,000 litres. And that's 24,000 litres of air that has already been compressed by 4 of the world's largest turbochargers.
The exhaust gases drive 4 humongous turbochargers. This is one of them. Fresh air is sucked from above decks along here into the turbocharger and reaches 3 times atmospheric pressure before entering the cylinders below.
The compression of all that air helps both the efficiency and overall power of the engine. The air combusts 9 tons of heavy fuel oil per hour, which is injected into the top of the cylinders.
Each cylinder has 3 fuel injectors. 1, 2, 3. The fuel combusts as soon as it enters the cylinder, driving the piston down.
At the bottom of each cylinder, the exhaust gases are pushed out through these holes, and the next cycle of compressed air is sucked in. Down another floor is the crankcase, where internal combustion is translated into propulsion power.
This is my favourite bit. You can only open this door when you're in port and the engine's switched off. There's the piston, connected to the massive, massive, massive crankshaft via the mother of connecting rods. It's amazing. Each compartment in this crankcase is the size of your average bedroom.
All that is controlled by one man in an orange boiler suit with a very sophisticated computer. With 90,000 horsepower at his disposal, he can maintain this ship at a steady 24.5 knots, 28 miles an hour, for weeks at a time. And he can get 1,000 miles to the gallon for every ton of cargo carried. Incredible.
Up here on the bridge, the captain can either use this control as a telegraph system or take full control of the engine himself. And over here, we have the ultimate in power steering. At 20 knots, this ship can do a U-turn in 4 minutes with a turning circle of half a mile across.
Fancy a joyride? This is a good bet. 10 million miles before this engine packs it in. That's about 400 times round the world.
Ships seem destined to keep getting bigger and bigger. And as the ships get bigger, so will their engines. And until someone comes up with something as robust, reliable and economical, the diesel engine will remain king of the waves.